So hello, everybody. My name is Suzanne King. I'm a professor in psychiatry at McGill and a member of the Mental Health and Society Division of the Douglas. And I'd like to welcome you to the first seminar of the Mental Health and Society Division seminar series. I will let you know that this is a do-over, that that we presented this seminar on Friday, January 22nd, 2001, with an audience, a nice audience, but we failed to record it. So Guillaume, Elgebili, and I are doing a do-over. So that's why there will be no questions or discussion afterwards. All right, so with no more further introduction, we'll get started. So this seminar is about testing and interpreting moderations and interactions. And so I'll just start at the very basics. So everybody pretty much should know what we mean by a zero order correlation. That is that some variable X, potentially a predictor of psychopathology, for example, is correlated or associated with some outcome Y. So that association could be positive, where if there's more of X, you have more psychopathology Y. It's also possible that that association could be negative, where more of this environmental factor X is associated with less psychopathology. But as happens actually more often than we would like, we find that there's no association, that the level of Y or the outcome is totally unrelated to the level of X. So, but what might be actually hiding below that non-correlation is some other variable W that might be moderating that association. So it's possible that if an individual or a group, say females, that for them it's a positive association, but for some other group it's a negative association. So W, this factor W, could be the moderator, and in the example I just gave, it could be sex of the individual. So these terms that are used, moderation, interaction, multiplicative association, are essentially talking about the same thing. Kind of the theoretical idea is that some condition or some characteristic W is moderating the association between X and Y. In order to determine if that's the case, one would test the interaction statistically, and then the way you would test it is by including a multiplicative interaction term to the regression. So some people talk about how if Y equals X plus W, that is an additive association. And then once you include that interaction term, then it becomes multiplicative. So in developmental psychopathology, we're very interested in these kinds of associations. So we want to know what are the factors that might increase risk for psychopathology. But then within there, we want to know, well, who is most vulnerable or who is most susceptible for psychopathology? And we might also want to know what are the conditions that might buffer an individual from some of those risk factors. So these are the kinds of questions that we're interested in. So in today's seminar, the way we're going to be introducing these ideas is by using an example from our own research to demonstrate these concepts and also the steps that we're going through. So the example that we're using is a study that was done by a research assistant in our lab, Erin Yang Ping, and the paper that was published in Psychoneuroendocrinology was prenatal maternal stress and toddler stress reactivity at 2.5 years of age, the Iowa flood study. So there's a lot of research on stress in pregnancy, and a lot of it does show that prenatal stress predicts offspring developmental problems. The underlying idea is for fetal programming that maternal stress hormones, glucocorticoids like cortisol, under periods of stress might cross the placenta and then affect the fetus, and in particular the fetus's hypothalamic pituitary adrenal axis, the HPA axis, and potentially influence the way the child, then will react to stress later in life. But the literature on prenatal stress is very inconsistent. So some people, when they're studying prenatal stress, they're looking at maternal depression or anxiety during the pregnancy. But that's not, neither of those are randomly assigned to women. So there's a big mix-up, a big entanglement between prenatal maternal anxiety and depression and genetics, for example. And another reason that this literature can be very inconsistent is that when people are studying a stressor, like perhaps exposure to some major life event, most of the time people are not able to separate out the effects of objectively what happened to the mother while she was pregnant from her subjective response to whatever happened. So her distress, if you will. So the objectives of Aaron's study were to determine the extent to which maternal objective hardship and subjective distress might explain variance in toddler cortisol when stressed by being separated from their mothers, so maternal separation. And then because in the literature, there's some literature suggesting that boys are most susceptible to maternal stress. Other studies suggest that it's more girls that are susceptible. Other studies suggest that it's boys. So an additional objective is to determine whether sex moderates the association between prenatal maternal stress and cortisol. So Aaron used the data that we have from the Iowa flood study in the summer of 2008. The Midwest was subject to a lot of flooding. I think it was rated like the 10th worst natural disaster in US history at the time. This is a picture from Cedar Rapids, Iowa. What you see here are bridges, some of which are completely submerged. Those bridges are over the Cedar River, and normally they're about 100 yards above the level of the river. So you can see that this was quite a devastating flood. So we recruited women who had been pregnant during the floods because we piggybacked on an existing study of pregnant women. We were up and running to recruit women within weeks of the floods. And so right away, we assessed each woman's level of objective hardship. So we created a scale that we called the Iowa Flood 100, the IF 100, because it was quite skewed. We had to take a log transformation of it. So when you see the log IF 100, that's the objective hardship that the women went through. We also assessed their subjective distress. We used the impact of events scale revised. This is a scale that assesses post-traumatic stress symptoms in the person. That also was quite skewed, so we had to take a log transformation. So when you see this in the upcoming slides, you'll know that this is the variable for the subjective distress of the mothers. So when the kids in this study turned 2.5, we invited them to come into a lab in Iowa. And at one point during the evaluation period, the mother just stands up and leaves the room. So of course, we had a two-way mirror, and the children were never in danger of hurting themselves. But we took saliva samples from those kids a few times before the mother left the room, and then a few times after the mother left the room, and then returned after like 3 minutes. And so from that, we calculated the area under the curve increase. So the total amount of cortisol that was secreted during this stressor. And the calculation that we used was the increase in cortisol from baseline. So essentially, we're looking at 4 different research questions in this study. The first is, does prenatal maternal stress correlate with child cortisol reactivity? as a function of this maternal separation. And if we look at the objective hardship of the mother, with all the children, it correlates 0.258. That was significant, but it's not very impressive as a correlation. And so we thought, okay, we'll look at males and females. But when we separate into these groups, again, the correlations are not very impressive. So then when we look at the subjective distress, so the mother's PTSD symptoms, once again, that correlation it's significant, but nothing to write home about. And especially in males, there's like nothing there. That's a totally non-significant correlation. But we saw in the females that there was a very strong positive correlation between the mother's PTSD symptoms during pregnancy as a function of the flood and how much cortisol the girls were secreting during the separation. So this is where we really want to bring in Guillaume's expertise in statistics. We learned about this macro that can be used in SPSS. It's called process. And with the process macro, we're going to answer a couple of additional research questions. First of all, we'll use it to determine, does sex moderate the effect of PNMS on child cortisol? So we'll test that interaction. So again, the multiplicative polynomial here, no, it's not a polynomial. The interaction term, IESR multiplied by sex. We'll use the process macro to test that. And then additionally, at what level of IESR is child sex actually associated with cortisol? So determining if there are regions of significance. Then we'll walk you through some additional analyses to determine if the pattern of interaction supports one of two hypotheses or neither of them. The first is the vulnerability stress model, and the other is differential sensitivity. Okay, so I will hand this over to Guillaume at this point, and I'll give Guillaume remote control. There you go. So take it away, Guillaume.
The unmute button moved, so I had to go after it. So in our lab, we tend to use the process macro to run those kind of interaction analyses, but mostly to investigate them further. The reason is that process can be used to probe the interaction to get to see what's a bit to dive deeper into the interaction to know what's really going on. So in this part of the presentation, I'll try to explain to you like what the process macro is and how to use it to run moderation analyses. So process is a free macro that Andrew F. Hayes created that can be used with SAS, SPSS, and soon R. It allows you to run moderation, mediation analyses, and much more. There are over 70 models that are already pre-configured into process that you just plug in the model number and it will know that you want to run moderation or mediation or moderate and mediation or a lot of different models. But with since version 3 of process, you can also create your own path analyses that you want to run, as long as they are regression-based analyses. Just a quick note that the process macro is a syntax. So you activate it through a syntax and never attempt to modify that syntax. You don't need to, and it will just create problems for you. So you can download the macro or the syntax at that link that's showed right here. I will now show you how to activate the macro. The idea with the process macro is that SPSS, process is not a default command for SPSS. So you have to teach SPSS how to use it. and so basically to activate it, and then how to properly run it. So to do that, there are 3 very simple steps. So the first step, well, step 0 would be to download the process macro. Now, step 1 is to open the macro, and that's it, would be a syntax file. Step 2 would be to run all the macro syntax to allow SPSS to understand what the command does and how to use it. And step 3 is to close the process macro syntax to avoid modifying it by mistake. Something I need to, a very important note here is that SPSS forgets how to use the process macro, the process command, every time it's closed. So every time you open SPSS again, you have to rerun those 3 steps to teach SPSS again how to use process.
Okay, so so the second research question is, does child sex moderate the effects of objective or subjective prenatal stress on child reactive cortisol? In other words, do the slopes of the regression lines, or those correlations between prenatal stress and cortisol, differ significantly for males and females? So that's where we turn again to process to answer that question.
So to answer that question, oops, okay. So to answer that question, we use process. That's no big surprise. So the next step is to add the process command to your regular SPSS syntax. So in your syntax, usually you'd have regression and so on that you can just click and point, drag your variables, and then paste it in your syntax. But with process, you cannot paste the process command in your syntax. You have to type it in. So you can see here in red that as any other command, it starts with process, and then you have a bunch of variables and other arguments that you add in. So I'll now try and teach you what those different parts are in a moderation setting. So this is a copy paste of the previous process command. So as you can see, the first word is process, as any other command in SPSS syntax. Then you have the Y variable, which is cortisol reactivity, the predictor variable X, which is the subjective distress, and W, the moderator, which is the sex of the child. Then you have a list of covariates that are separated by space. And then you have the other arguments. So model equals 1 is the model number for moderation analyses. Plot equals 1 will tell SPSS that you want in your output to have a list of coordinates that you can use to easily plot your interaction graph. So I'll show you where it is later in the upcoming slides. And then Jane equals 1 is a very nice little thing. So in this setting, with sex of the child being dichotomous, so 0 for males, 1 for females, SPSS will give you if the effect of distress on cortisol is significant, well, what the effect is for boys and girls, and if it's significant for boys and for girls. But when you have a continuous moderator, you might want to know at which point in the moderator the effect of the predictor on the outcome becomes significant. And that is what Jn equals 1 will tell you. We'll show you an example of that later. So here's the output. from process. So as you can see, there's the left and right parts here. The right section usually is below, but I had to cut it so that it fits in one slide. So I'll walk you through the output now. So the first section at the top is the model presentation. They're presenting the model. So you have your outcome predictor and moderator with the variable names, the list of covariates that you want to include, as well as the sample size for this particular regression. Then you have the model summary and the ANOVA from the ANOVA table that you'd get in a regular regression with SPSS. So you have the outcome variable name, as well as the R square, so the amount of variance explained in your outcome by the whole model, as well as the significance of this model. Then underneath you have the coefficients list. So you have for each variable what's the coefficient from the regression and the p-value for that coefficient. So you can see that the interaction term is significant in our example, meaning that there is, so the effect of subjective distress on cortisol reactivity is different for boys and for girls. So now we want to investigate it further, want to know, is it significant in boys or in girls or both, and so on. So here, the next section is the interaction. They present additional information on the interaction, including the R-squared change. So how much variance is explained by the interaction term. How much variance in the outcome is explained by the interaction term that is not already explained by the rest of your model. And you can see the p-value here, which is the same as in your model. But up until that point, you can get all of that information without process in a regular regression, with a linear regression command in SPSS. So the next part is what's really interesting with process. So here you have, and like the next section is what we call interaction probing. So it's all the section about diving deeper into the interaction to see what's going on in there. So here you can see that we have for each level of the moderator, so for boys 6 equals 0, girls 6 equals 1, you have the effect and the p-value associated with that effect. So for boys, you can see that we have a negative effect that is not significant, but for girls, we have a positive effect, which is significant. And this fits with the correlations that we saw earlier that Suzanne presented. The next section is the plot equals 1 section. So you'll have, this will give you coordinates that will allow you to easily plot the interaction to really see what's going on. I usually use Excel to plot those interactions because it makes nicer graphs, in my opinion. So what you see here is that you have the subjective distress coordinates here. So that would be the x-axis, and the cortisol reactivity variable here. So it would be the predicted cortisol reactivity based on your model. So, and here in the middle is sex of the child. So you have males and females below. So basically those two variables, those 0 and 1 would be your males and females, would be your two slopes. And then for each of those two slopes, you have your x coordinates on the left and your y coordinates on the right. So you'll see here the figure that it creates. So you can see subjective distress on the x-axis, AUCI, so cortisol reactivity on the y-axis, and males in blue, females in red. And you can see from what we gathered here that males the effect is not significant but negative, and for females it is positive and significant from the start. So to summarize all of that, it helps us to answer research question 2, which is the effect significant? Well, was the effect different between males and females? Yes, because interaction was significant, but also is the effect significant in males or females? And you can see here that it is significant in females only. So the effect of subjective distress on cortisol reactivity is significant in females only.
Right, so that takes us to research question number 3. So at what level of IESR is child sex associated with cortisol? So in other words, under what conditions are there sex differences in the association between prenatal maternal stress and child cortisol? So we move on.
So this question here is basically reversing the theoretical question. So the first research question 2 was what's the effect of subjective distress on cortisol reactivity at different levels of sex? And here the question is, what is the level of sex? What is the effect of sex on cortisol reactivity at different levels of subjective distress? So in the theoretical setting, we switch what the predictor and the moderator was. So how to test for that basically is only with process. You change what the X is and what the W is. So X becomes W. So the predictor becomes a moderator, the moderator becomes a predictor, and you're good to go. So this is the output that we get. So as you can see at the top, you notice that the predictor is now sex, the moderator is now subjective distress, but everything else right here stays the same. So mathematically, when you switch what the predictor and the moderator is in a moderation setting, it doesn't change the interaction. It doesn't change the overall model and its coefficients. It's more of a theoretical understanding of your model. But what's really interesting is the next section. So as you can see, before we had is the effect of distress significant for boys and for girls. Now we look at is the effect of sex significant? So this is the effect of sex of the child, and if that effect is significant at different levels of IESR. So this section here on the right is what we get with Jn equals 1 that I showed you earlier. So here you can see that, so Jn stands for Johnson-Niemann, in case you were wondering. So you can see that those two values here are the value of IESR, so the value of subjective distress, at which the sex difference in terms of cortisol reactivity becomes significant. So the first value, 0.39 on the left and 3.46 on the right. And you can see here that you also have the percentage of your sample that is below and above that point. So on this graph, so those 2 points here delimits what we call the regions of significance. So there are those regions highlighted in blue here on the left and the right, and they're the regions for which the difference between boys and girls in terms of cortisol reactivity is significant. So you can see those 2 regions here are highlighted in this table. So yeah, let me explain what this table is first. So you can see that for many different levels of subjective distress, you have the effect of sex, and the p-value for that effect. So you get this table when your moderator is continuous and you ask Jn equals 1 in your equation. So back to the regions of significance, you can see here that below 0.39 here for those three values, you have p-value below 0.05. And for those values above 3.46, you have a significant coefficient as well. So you can, those values here are represented by those, the blue shaded region here on the graph. And as you can see, the effect is negative on the left side and positive on the right side, meaning that on the left side, males are significantly higher cortisol reactivity than female, but it's switched on the right-hand side. So females have higher reactivity than males. So here's a little summary of what we could get. So for what we learned from process, so basically the research question 3 was, under what condition do cortisol in males and females differ? And we could answer it with process. So that the difference in cortisol secretion between males and females is significant in participants whose mothers had very low on the left-hand side or high on the right-hand side PTSD-like symptoms. And this is the final regression interaction graph that we present, for example, in the paper.
Yeah, so then we move on to research question number 4. Does the pattern of the interaction support either of two hypotheses about moderations in development? So there are at least two important models or hypotheses in developmental psychopathology. And one of them is the vulnerability stress model that suggests that most people are probably not terribly susceptible to this, this particular risk factor, or not so much vulnerable, but some people, either through their genotype or something in their brains, that the more there is of X, the greater their risk of Y, or the more severe their psychopathology. So this suggests that really it's just a question of being vulnerable or not vulnerable. But the other model is suggesting that it's not so much that one group is vulnerable. So basically they can only go between kind of normal and being abnormal. It suggests that rather than being vulnerable, that this other group, this W1 group, is just sensitive to these risk factors. So differentially sensitive, such that they're simply more sensitive to, in particular, this environmental effect. So when the environment is very good, let's say they have much less psychopathology than the other people, but when the environment is bad, they have much more psychopathology. So the kind of the phrase that exemplifies this differential sensitivity or differential susceptibility is the idea of for better and for worse. So we do see that sometimes in our results, and it confuses us because we're used to thinking about vulnerability stress, but now we have a model that kind of explains this. So it's all very well and good to see your results and look at the graph, and sometimes it's really obvious that something is vulnerability, reflecting or supporting a vulnerability stress model or supporting a differential sensitivity model. But even better would be to do a statistical test to see if your data support one or the other of these models.
So this brings us to the crossover point analyses. So first of all, I'll explain to you a bit what it is, and then I'll explain to you how to use it. Oops. Okay, so here the goal is to, like Suzanne just mentioned, to determine statistically if we have differential sensitivity or vulnerability stress, or if maybe neither of them are supported. So the first step here is to find the crossover point estimate, which is here highlighted circled. So it's the point in on your graph where the slopes cross over each other. So this is the first step, but it's not the final step, because we should not use that to determine if we have differential sensitivity or vulnerability stress, because it's the same as looking at a regression coefficient without a p-value. So you have an estimate that is specific to your sample, but you don't know if that estimate is significantly different from, if that coefficient is significantly different from 0, so you're not sure if we have DS or VS. So what we do then is to try and find the confidence interval around that crossover point estimate, which is a second step. In this presentation, I'll use this symbol here to show the confidence interval range. And it basically represents the range of the most probable values that you could find in the population. So if all the, so we'll compare this confidence interval range with the range of the predictor X, in this case, subjective PNMS. And that will give us information about whether or not we have differential sensitivity or vulnerability stress. I'll show you the 3 possible scenarios in the following slides. But first, I'll go over how to calculate the crossover point value, which is the more mathematical slide. So we only have 2 slides, so it shouldn't be too bad. But it's important. So the regular traditional way of presenting the regression formula with a simple moderation model with 2 covariates is the following. So you have y, which is the outcome, or and then, so the outcome would be equals to a sum of coefficient multiplied by their variables. So B0 would be the constant, and then the first coefficient times the moderator plus the second coefficient times the predictor plus the third coefficient times the interaction term plus the series of covariates. So through algebra, there's those wise and smart people that were able to determine the crossover point. So basically, from this formula, they were able to find at which point those 2 slopes crossed over. So it is, so yeah, right there. So it's computed as, we note it as C, and it's computed as, or calculated as minus the moderator coefficient divided by the moderation coefficient. So in this case, it would be minus B1 divided by B3. So here in our example, we get 1.497, which is exactly what we get on this graph. So it's comforting that we did not make a mistake. Then the second step is to compute the confidence interval, to find a way of computing or finding what the confidence interval is, to know what if it's differential sensitivity or vulnerability stress. So to do that, you have to create a formula that includes the crossover point C. So to do that, those same smart people were able to find this formula. So basically, you substitute some terms in the regression formula with C, and you get this. So it looks much more complicated than the previous version because it is. It's no longer a linear regression. It's a nonlinear regression. And to do that, you have to use a software, but SPSS can handle this. So that's a good news. So here, the first, looking for my word, the first scenario is differential susceptibility hypothesis. So in this scenario, just a recap, it's the for better and for worse scenarios. So differential sensitivity hypothesis. So it suggests that some people will suffer from a high stress environment here, but will fare much better in the better environment. So lower stress. And in terms of graphs, it's represented by an X shape. So you can see the X right there. So how to determine if we have differential sensitivity is to basically the idea is that the confidence interval for the crossover point will be, all of it will be within the range of your sample predictor range. So if we use the confidence interval representation here, the whole of the confidence interval will be within the range or the limit of your subjective distress. So as you can see, when we move the crossover point within the confidence interval range, we always have an X shape. Sometimes it's skewed, but it's still an X shape. So this means that no matter where your crossover point is in the population, you'd always have an X shape, which suggests differential sensitivity. The second scenario is vulnerability stress. So this on a graph is represented by a V shape or smaller or greater shape. And the idea for vulnerability stress is that some, but not all, are vulnerable to stress. So in order to test for this, or the idea is if the crossover point confidence interval is outside, the whole of the confidence interval is outside the range of your predictor, then it supports the vulnerability stress hypothesis. So you'll see the crossover point is the red dot right there. And as it moves within the range of your confidence interval, you always have that V shape, or that V shape. So no matter what's the real the real crossover point in your population, you always have vulnerability stress. So it supports this hypothesis. The third scenario is when it does not support any of those two hypotheses. So whenever you have a crossover point that is close to the boundary of your predictor's range, you're not sure if you actually have an X shape or a V shape. So neither of those hypotheses will be supported if the crossover point overlaps partially with the range of your predictor. So you can see as the red dot will move within the confidence interval range, it shifts from a V shape to an X shape. So in the population, we don't know what's the real shape in the population, so we cannot support either hypothesis. We had one question during the presentation. In our example, we have regions of significance on both sides. So doesn't that suggest differential susceptibility? Usually it does, but it's always nice to have a test that actually tests for this hypothesis directly. And we could have had a next shape. Let's just go back. So try to go back. So in this example here, let's, like, if there's no region of significance on the left, we don't, and only one on the right, we wouldn't know if we have DS or not. So we actually have to test for this crossover point analysis to actually be able to support that scenario. So back to the, oops, there you go. Back to Suzanne.
Right. So as we mentioned, we can also have a continuous moderator. So for this, I just wanted to give a different example. My doctoral student, Benji Daniel, also looked at these children from the Iowa flood study, and she wanted to know, this is one of her research questions, whether prenatal maternal stress predicts externalizing problems in the children when they were 4 years old, and whether or not the quality of parenting might buffer the effects of the prenatal maternal stress. In particular, she was looking at the consistency of discipline that the mother espouses in a questionnaire. So for this question, does consistent parenting buffer the child? This was one of her output graphs. And so we can see that we've got, this time it's maternal objective exposure, or her objective level of hardship from the floods. That's our predictor variable. And what process does is it, when it goes to plot this, because of course we no longer have males and females, a dichotomy, we've got a continuous variable. And I can never remember, Guillaume will correct me, but I think these lines are for the top 85th percentile and the lower 15th, is that right? You're muted, Guillaume.
Yeah, it's for the 16th and 84th percentile.
Okay, 16 and 84 instead of 15 and 85. So pretty close. So the way the parenting scale works is that high values represent inconsistent discipline, and low values reflect consistent discipline. So what we can see here is that we could conclude that better parenting does buffer the child. So we can see that when parenting is consistent, there's no effect whatsoever, no significant effect of the prenatal stress on the child's externalizing problems. But for kids whose mothers are inconsistent in their discipline, greater prenatal stress was associated with more of these externalizing problems. Now, I just want to say that we were tempted to look at these models of vulnerability stress or differential sensitivity, but decided that it wasn't really relevant, that we couldn't say that the parenting, the environment when the children were 4 years old would make them more or less sensitive to something that happened to them during their pregnancy. So it didn't seem to really reflect hypothetically, theoretically, what we were after. But it does answer this question of whether parenting buffers prenatal stress. So in the process of doing Benji's dissertation, we thought, well, let's turn this interaction around, because of course every interaction you can statistically just switch around what is your predictor and what is your moderator. So in this graph, we've got the consistency of discipline, where high values on this scale reflect more inconsistent discipline. And the lines, so the orange line now is for high levels of prenatal objective hardship, and the blue is for low levels. And here the results would suggest that what we have is a situation of differential sensitivity, where the prenatal maternal stress, high levels of objective hardship in the mom during the flood, during her pregnancy, is associated with more problems in the kids. But when there's very little, okay, so I'm just going to skip over. So the crossover point analysis actually supports the differential sensitivity hypothesis and not vulnerability stress, to where these kids who had high levels of objective hardship during the pregnancy, they actually do better. They have less externalizing problems in a good environment with very consistent parenting, but they have more problems than the other group when there's very inconsistent discipline. So I hope that distinction is clear. So that's the end of our presentation, because we have no audience and we don't know what questions to ask. If you do have questions or comments, please feel free to connect with us, and you can contact us at our email addresses there. Guillaume, I don't know if there's any final word that you want to give.
Not that I can think of. All good.
Okay, so that's great. I'll go back. And so thanks very much for your attention. And yeah, if you want copies of the slides, you can just email us. So thanks very much. And I hope it is useful. Bye-bye.